All right, kids, as promised, here are your results to the November 22nd paper one. All right, so number one says, how many oxygen atoms present in 0.05 moles for barium hydroxide hydrate? So the first thing we got to do is see how many, because if this was 1 mole of that, we got to see how many oxygens. So 8 for the water and 2 for the hydroxide. So that ups to 10 oxygen atoms per mole of this compound. So 10 per mole, if I have 0.05 moles, I just multiply that by 10, and that'll tell me how many I have in 0.05 moles. And of course, 10 times 0.05 equals 0.5. So I have half a mole of oxygen atoms in 0.05 moles of that compound. Times Avogadro's number will tell us how many atoms it is, and 6.02 times 10 to the 23rd times a half is 3.01 times 10 to the 23rd, or choice A. Number two says, what is the change of state from gas to solid? So that probably was mentioned at some point during the year, but you may have forgotten. The answer is deposition. If you didn't know that, there's a good way to figure it out. Figure just what everything else is. So condensation is gas to liquid, freezing is liquid to solid, sublimation is solid to gas. So process of elimination will tell us choice B. For number three, it says how many moles of carbon dioxide are produced from the complete combustion of 7 grams of ethene. So please remember, if you're given an amount of one substance and asked how much of another substance forms, that is a stoichiometry problem. So in order to do stoich, we need a balanced equation. We're going to fully combust ethene. So my equation will be C2H4 plus oxygen. Complete combustion makes CO2 and H2O. So when we balance, it's going to be a 2, a 2, and a 2. So for every 1 mole of ethene, you make 2 moles of carbon dioxide. I have 7 grams, so 7 divided by the molar mass will give us the number of moles of ethene we have. 7 divided by 28 is 1/4, or 0.25. I have 2 moles of CO2 for each of that, so that would be 0.5 moles. Strike. All right, so number 4 says successive ionization energies of X are shown. What energy is required for element X to reach its most stable oxidation state? Well, you'll tell that it's at its most stable oxidation state when you see a large jump in ionization energy. So to lose 1 electron, it's 740 kilojoules. To lose a second, it's 1450. To lose the third, oh, big jump there to 7730. That means after the loss of the second electron, we will have its most stable or noble gas electron configuration. So a lot of kids are going to want to choose 1450, but remember that in order to lose the second, you have to lose the first. So it'll be 740 plus 1450, which is 2190. So which quantities are different between the two species represented by this notation? So we got a tellurium atom and an iodide ion. So here's our atomic number. Protons are obviously different because I have 52 in tellurium and 53 in iodine. To get the number of neutrons, it's the mass number minus the atomic number. Since they have the same mass number but different atomic numbers, that means neutrons will also be different. And in an atom, the number of electrons is equal to the number of protons. And in the ion, if it's an anion, we have to add the charge to get the total number of electrons. So tellurium would have 52 electrons, and the iodide ion would have 54. So that's protons, neutrons, and electrons, choice D. So number 6, which best explains why complexes of D block elements are colored. So this is a little bit different than the formation of the emission spectrum. Remember, when the ligand bonds to that transition metal cation, it splits the d orbitals into 2 discrete levels. The absorption of light causes the electron to become promoted, and if it absorbs light, the rest is reflected. So the answer is A. Light is absorbed when electrons are promoted between d orbitals. So just think about how anything transmits color to your eye. If something appears green to us, that means it's absorbing all the colors except for green, which it's reflecting back to our eyes. So they're colored because of the absorption of light, and whatever is not absorbed, the complementary color, is what we would see. 7, which are metalloids. For that, we need our periodic table. Our periodic table has a stair line essentially on it, like this. Elements that touch the line are semi-metallic, with the exception of aluminum. So silicon, germanium, arsenic, antimony, tellurium, and astatine. I believe polonium is also metallic in nature. So let's go ahead and look at our options here. Gallium, nope, not on the line. Germanium and arsenic are, so 2 and 3. Which property of elements increases down but decreases across? That is atomic radius. Think of a snowman increasing down, decreasing across. Which molecule can be represented by resonance structures? Remember when we taught resonance structures in topic 4, the thing we used to show resonance was typically either ozone or our polyatomic ions, nitrate and carbonate. Remember, to have resonance, you have to be able to essentially move the location of the double bond without rearranging the atoms themselves. So we could just as easily have that double bond be there or there. And so the only compound here that has the nitrate ion is nitric acid. Which elements are capable of forming expanded octets? To form an expanded octet, you need to have some partially occupied d orbitals. So any element that's in period 3 or later can do so. Generally the nonmetals, because they're more likely to form covalent bonds. So nitrogen is in period 2, phosphorus and arsenic are big enough, so C. Which molecule has a tetrahedral geometry? So like nitric acid is a combination of a hydrogen ion and a nitrate ion, so that's really kind of sort of an ionic-y bond, so it would not create a tetrahedral arrangement. Think of it more like H plus attached to the nitrate ion. The nitrate ion itself is planar, but it's the electrostatic attraction between those things that makes the bond. Now, the xenon compounds don't fit the bill because xenon already has 8 valence electrons, so both of these compounds would actually give you a square planar shape, so SF4. Alloying a metal with a metal of smaller atomic radius can disrupt the lattice and make it more difficult to atoms to slide over each other. Which property will increase? So remember, copper is pretty malleable. So we don't use copper to make bells. But if you take tin atoms and mix it with the copper, you make bronze. Bronze is much stronger. So actually making an alloy will decrease malleability, decrease ductility. Conductivity, well, different metals have different conductivities. So if you're mixing 2 metals of different conductivities, I would assume it would bring the conductivity of the more conductive one down and the less conductive one up. So we can't say that's a straight increase or decrease, but that bell made of bronze is much stronger than the bell made of copper. Number 13, chlorofluorocarbons contain bonds of the following lengths, which is the increasing bond strength. So remember, the shorter the bond, the stronger it is. So the shortest bond is CF, so that's going to be the strongest. The shortest bond, or the longest bond is the carbon-chlorine, so that'll be the weakest, putting the carbon-carbon in the middle. So that to me looks like choice C. Number 14. What is the value for the enthalpy of formation of methane from the given enthalpies of combustion? So this is a Hess's law problem where we manipulate our equations. I'll call this one A, that one B, that one C. Only difference here is we're not given the overall equation, but we're told it's the enthalpy of formation of methane. So remember, the enthalpy of formation is the energy released when 1 mole of a compound is produced. Since our compound is methane, we look at the elements that make methane, which is carbon and hydrogen. In order to balance hydrogen, we put a coefficient of 2 in front. So now let's go ahead and match. I see in equation A, I have copper. It's in the right spot, and it has the right coefficient. So when we calculate standard enthalpy change, we're just going to input the value for A. Next thing I see is hydrogen. It's on 2 moles on the reactant side in the overall. Here it's 1 mole on the reactant side in the step, so we have to add 1/2 the value of B. And then finally, I have 1 mole of methane on the product side. Here in equation C, I have 1 mole of methane on the reactant side. So I'm just going to add the negated value for C. Now let's substitute in the numbers. A is negative 394 plus 1/2 or 0.5. Hang on a second. No, I'm sorry, I said half. I have to double that. Double it, not half it. Sorry, double it. Anyways, B is negative 286, plus the negated value for C, so plus 891. The only one that matches up with that, remember, that's negative 286, so that is correct. D is your answer. Number 15, which magnitudes of lattice enthalpy and hydration for an ionic substance would result in the most exothermic enthalpy of solution? So remember, lattice enthalpy is the endothermic process, and enthalpy of hydration is the exothermic. So the lattice enthalpy, breaking it, takes energy, and energy is released when the ions are hydrated. So what we want is a small endothermic process and a large exothermic process. Will be exothermic if the amount of energy released is greater than the amount of energy taken. So C matches up with that. Small lattice, large hydration. Which alkane has the lowest standard entropy? All right, so this one is unlike any that we've looked at in class. We do know that changing state from liquid to solid to gas increases entropy. Increasing the number of particles increases entropy, but here we have 4 gases, and since it's standard entropy, we're talking about equal amounts, 1 mole of each. So the real only thing different about these compounds really is the amount of potential energy they contain. That potential energy is stored in the chemical bonds. Since methane has the fewest number of bonds, it has the lowest potential energy, and lower energy in that case would lead to lower entropy, more stability. Or less stability, more stability. Okay, so at which temperature could delta H, delta S, and delta G all be positive? Well, remember, if delta H is positive and delta S is positive, then this reaction will only be spontaneous at higher temperature. So if it's non-spontaneous, delta G is positive, which means this would be that all 3 of those would be positive at low temperatures. So if it's negative at high temperature, then it'd be positive at low temperature. What is the initial rate based on this graph? So remember, to get the initial rate, first of all, it's the rate at time equals 0. The first measured data point. To get the rate, we take the slope of that initial line. So the change in y is 0.2 divided by the change in x, which is 1, 2. 0.2 divided by 2 equals 0.1, so the answer is A. Number 19, what changes would increase the rate of an exothermic reaction? Well, exo, endo, doesn't matter. If we want to increase the rate, we want high temperature, high concentration, small particles. So we would increase the temperature and decrease particle size. Number 20, data is given for this reaction. We're given some initial rate data. Which rate equation can be inferred? So again, we have to compare. I have to find 2 rows where one stays constant and the other changes. So as x stays constant, as we double the concentration of y, the rate remains constant. That means it's 0 order with respect to y. I would go on, but C is the only one that shows y with a 0 order. Number 21, activation energy of a reaction can be obtained from the rate constant and the absolute temperature. That just means the Kelvin temperature. Which graph of these quantities produces a straight line? If you remember, it's a plot of the natural log of the rate constant versus the 1 over the absolute temperature, so D. Number 22 gives us a reversible reaction, gives us the equilibrium concentrations. Says what is the value of K? This is a pretty easy one, so we just need the equilibrium constant expression. It'll be ICI cubed squared divided by I2 divided by Cl2 cubed. Let's put in the numbers now. So that would be 2.0 squared divided by 2.0 times, oh wait, 0.20, my bad, 0.20 times 0.20 cubed, so let's simplify everything. 2 squared is 4, 0.2 is just 0.2 times 0.2 cubed. 0.2 times 2 would be 0.04, times 0.02 would be 0.004. So here I'm displaying my mathematical ineptitude. I'm just going to use a calculator here because I'm not trying to make this video that long, and I don't want to show off how bad I am at stupid math. So, 2,500. So, what I would say is this is going to be integer denominator divided by a really small denominator, so you can automatically get rid of that one and that one. And then from there it would just be some kind of like 4 divided by 8, which is a half. I don't know. I'm moving on. All right, so for number 23, it says which of these changes would shift the equilibrium to the right? So if we look at choice 1 and 2, it's dilute HCl or concentrated HCl. Well, if we look at our equation, if we're adding dilute HCl, yeah, we're going to be increasing the concentration of chloride ions. But remember, a dilute solution is mostly water, so we'd also be adding a product. So chances are either the addition of the 0.1 molar wouldn't do anything or would actually push it in the opposite direction. So that won't be it. If we add concentrated HCl, that will massively increase the concentration of chloride ions, pushing it to the right. And if we evaporate water, that's like removing a product, so 2 and 3 would do the trick. So the answer is C. For number 20, equal volumes of 0.1 molar weak acid is titrated with 0.1 molar weak base, which is the same for the two acids. So weak versus strong doesn't change the stoichiometry. If they're both monoprotic acids and you start with the same concentration, it will take you the same volume of base to neutralize. Which species has the weakest conjugate base? If it's the weakest conjugate base, then it means it's the strongest acid. Water can act like an acid, but it's weak. The hydrogen carbonate acts like an acid, but it's weak. Ammonium acts like an acid, but it's weak. HCl is the strongest acid in the group. Which solutions will make a buffer? So it looks like choice A, remember, to make a buffer, we either need a weak acid and a salt with its conjugate base, or we need to partially neutralize a weak acid or a weak base. So in choice A, we got strong acid, strong base, so that won't do. In all the other ones, we have weak acid and strong base, so those would all work, but we just have to choose the one in which the base is the limiting reactant. So here we have equal moles of acid and base, so that would be full neutralization. Here we have 0.05 moles of acid and 0.1 moles of base. That would put the base in excess. Here we have 100 cubic centimeters of weak acid and 50 cubic centimeters of equimolar weak base, so that would do the trick. If you couldn't tell, I'm trying to go as quickly as possible just so this isn't forever. Which species can act as both a Lewis acid and a Lewis base? Remember, to act as both, you got to either be able to accept donate a pair of electrons. So water can do that. Water can act as a Lewis base during the formation of a hydronium ion, and it can act like a Lewis acid during the formation of a hydroxide ion. Ammonium is complete, the nitrogen is completely surrounded by hydrogen. It can't accept any more electrons. Same thing with methane. And copper 2 don't have no pairs to donate. So what occurs during the operation of a voltaic cell based on this reaction? So I see chromium is oxidized and iron 2 is reduced. That makes my process for chromium at the anode, and my process for reduction, or for iron, is at the cathode. So the electrons always move from anode to cathode, so the electrons move from chromium to iron, yes indeed. And then the iron ions move toward the iron electrode where they are reduced into iron. So the answer is B. For number 20, it gives us a completed unbalanced redox equation. It wants to know what the coefficient for H plus is. Best way to do that is to pull it apart into its half equations. So for the oxidation half equation is going to be lead going to lead 2. To balance, we only need 2 electrons. In the other equation, I have nitrate going over to nitrogen monoxide, so I have to balance by adding a couple more waters, and then I have to put 4 H plus over here, and then total charge over here would be plus 3, so I need 3 electrons here. So to balance, I'd have to multiply that one by 3 and this one by 2. That's going to give me 8 H plus, so D is our answer. Ugh, I hate this question, but I think I finally figured it out. So it gives us 3 half cells involving chromium, and it wants to know which statement is correct. So in order to calculate the cell potential, we're going to take the voltage at the cathode and subtract the voltage at the anode. In class, we talked about reversing the oxidation process and adding it. This is the same exact thing mathematically. So let's first look at chromium 3 oxidizing chromium 2. So if chromium 3 is doing the oxidizing, then it's being reduced. So that's what's happening at the cathode. And this is the process happening at the anode. So if we look here, chromium 3 being reduced is negative 0.744. The only equation showing chromium being oxidized is the top one. So when we subtract away negative 0.407, I ran out of space, you're going to get a negative value for there. And in order for it to work, you have to get a positive value. So no, it cannot oxidize chromium 2. But I'm going to finish this choice because what you're going to see is completing choice A will actually lead you to the right answer. So for chromium, here we have chromium being oxidized. Here we have chromium 3 being reduced. So when I calculate the voltage of that cell, it's going to be negative 0.744 minus negative 0.914. That will lead to a positive voltage, which means that process, ding, will work, which is the opposite of choice B, where chromium 3 cannot oxidize chromium 2, but it can chromium. So yay, I finally figured it out. All right, which factors affect the amount of moles at the product during electrolysis? The charge on the ion, yep, because if it's a lower charge, it doesn't need to absorb as many electrons or gain as many electrons. Molar mass is not relative. And time. The longer you do it, the more you're going to get. So 1 and 3. Which of these are isomers of pentane? So in order to be isomers, they also have to have 5 carbons. This harkens back to when I said during our organic unit that, you have to be able to actually interpret skeletal formula. So choice 1 here has 1, 2, 3, 4, 5 carbons. Hey. Choice 2 has 1, 2, 3, 4, 5 carbons. Yay. Choice 3 has 1, 2, 3, 4, 5, 6. So 1 and 2 only. Answer is A. All right. Coming right up on the end. Going forward, this is stuff we're going to talk about in our Unit 10 lessons. So for now, I'll just tell you which compound has a chiral carbon. In order for a carbon to be considered chiral, it itself has to be bonded to 4 unique atoms or groups of atoms. So all secondary halogenoalkanes will give you Well, at least all secondary halogen alkanes with more than 3 carbons will give you a chiral carbon. So the reason why it can't be propane is because this carbon would be attached to bromine, a hydrogen, and 2 methyl groups. But with the 4th carbon, now it's a hydrogen, a methyl group, bromine, and an ethyl group, meaning 2-bromobutane is the correct answer. Which conditions best favor the oxidation of primary alcohols to carboxylic acids? Remember, if you distill, you get the aldehyde. You need to reflux to get the carboxylic acid. If you want to make sure that all your alcohol is oxidized, you're going to want to use excess oxidizing agent. Which statement best describes retrosynthesis? I would just assume retrosynthesis would be the opposite of synthesis. I've actually never even seen this stupid term before, so I got to look in the guide to see where it appears. So the reaction conditions needed to convert the product of a reaction back to the starting materials. I would say those would be like retro conditions, right? The term synthesis does not describe the conditions, it just describes the reaction itself. So synthesizing a target molecule by working back from the target to the starting materials, that to me sounds like the most correct answer. Which combination of reactants will convert nitrobenzene to phenylamine in 2 steps? So the first thing we got to do is mix with concentrated HCl and either tin or nickel, and then deprotonate with a base. So A is the best choice here. C and D are if we wanted to oxidize an organic compound, and that's not what we're doing here. That's actually reduction. All right, a well-tested scientific idea has been used to make predictions, and it cannot explain a particular event. Which statement describes the approach to this dilemma? So this actually happened. Well, it happens all the time, but Isaac Newton basically developed all the equations to understand gravitational forces, and for hundreds of years, Newton's laws, and let me be clear, they're still used to this day, but they could be used to predict the rotation of planets. So you could use those equations to say, well, in 200 years, where will this planet be on this particular day? And they work. But what we found was the orbit of Mercury did not fit with Newton's laws. So Einstein came along and developed his general theory of relativity, which explained everything that Newton explained, but also explained why Mercury behaves the way that it does. So the hypothesis is what we have before there's a theory at all. So if we already have a theory and something else contradicts it, we would revise that theory. That's how science works, kids. All right, so what information about 2-hydroxybutanoic acid can be inferred through mass spec, infrared, and HNMR spectroscopy? This is just knowing what our machines do. The mass spec just gives us mass data, so it would give us the molar mass of the compound. It wouldn't tell us necessarily about which groups it contains. Infrared tells us which functional groups are present, but not how they are arranged in the molecule. So it would not tell us which carbon atom it's on. That's what NMR is for. So A is the correct answer. Mass spec gives us mass. IR tells us that it's got carboxyl and hydroxyl, and the NMR tells us where they are. What information can be deduced about a compound through X-ray crystallography? That's bond angles. Bond angles. Also bond length. And finally, we got an NMR here. It says which organic compound has the NMR shown. So first thing I see, 3 peaks. So we got to have 3 environments. Methanal only has 1 hydrogen environment. Ethanoic acid only has 2. Methyl ethanoate, actually draw it so that you can see it. Methyl ethanoate also has 2. Propanoic acid has 1, 2, 3, so it must be propanoic acid. Well, that's it, kids. Some tough questions on there, but overall not too bad of a paper in terms of how they go. So hopefully you work through the best you can, and hopefully you're able to learn a thing or two from this explanation. And thank you so much, as always, for watching.